All right, how's everybody doing? Welcome back to Math for Healthcare video lecture series. Today we're going to be working on counting still. Last time we saw permutations, and which is really an extension of the multiplication principle. Here we're going to be looking at combinations. I do want to remind you that the reason we're doing the counting is so that we could find probabilities. Because if you remember, we find the probability of things, we got to find the size of the sample space and the size of the event of it happening. And when you're doing these counting problems, you're really counting, when you count the number of ways to do something, you're counting the set of ways to do something. So the idea is to better prepare us with probability so we could better understand how we're measuring against randomness. So before or last lecture we talked a bit about permutations taken hour at a time. So I want to start with a couple examples to review and then we'll get into combinations. Okay? Now, so a baseball team has 9 players. How many ways can their batting order be arranged? Go ahead and hit pause, try this on your own. But this, we could think of it as, well, oh boy. We could think of it as 3, 4, 5, 6, 7, 8, 9 dashes. Right? How many ways are there to choose the first person? 9. Now the second person, it can't be the first person, so now there's 8, 7, 6, 5, 4, 3, 2, 1, which is equal to 9 factorial, which if we want a number, I'd use Desmos. Over there on the left, you can see what I use here is, oh, that's a good question. I haven't used the factorial button yet. There we go. 9, and just type in that exclamation point for factorial, and we get there's 362,880. Okay? Now that's a baseball team with 9 players in their batting order. What if I ask, what if the team has 20 players and 9 batters? In other words, how many ways there to have a batting lineup, batting order, when you're choosing from 20 players, but 9 are only playing at a time? Well, now, if we recall, hopefully recall from last time, we're going to use the permutations with repetition here. Why? There's 20 ways to choose the first person. There's 19 ways to choose the second, but you're only going down 9, right? Because you only have 9 players. So that's going to be the permutations of 20 things taken 9 at a time. So there's some orderings here, right? It's going to be 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12. But instead of thinking about that big long list, we're going to take advantage of Desmos. And here you type in n lowercase, capital case P, lowercase r. And then in parentheses, we're doing 29. And here we get 6.09 times 10 to the 10th. So the number grows quite a bit there. 10 to the 10th is quite a big number. But that's, hopefully remember those permutations of 20 things taken 9 at a time. Next up, let's say suppose we have 8 people running for office. How many ways to rank your top 3 choices? Well, let's see. We got 8 ways to choose the first person, 7 to choose the second, and 6 to choose the third. And notice here, let's say Andy, Bill, Cindy is different than Bill, Andy, Cindy. Right? That's 2 different things. All right? So 8 times 7 times 6. So there's 8 times 7 times 6, which is the permutations of 8 things taken 3 at a time. Just for practice, we're going to use Desmos for that. And PR of 8, 3. So that's 336 ways. Now, what if I change this question and says, how many ways to pick 3 people? So now we're not distinguishing. So now these two things are the same. Well, the reasoning goes is, well, we take all those same 8 times 7 times 6 that we had before, but we want to unorder them, so we divide by the 3 factorial orderings of these things, each of those 3 things. And we call this is the choose function, so C of 8 choose 3, or I write it a lot this way, 8 choose 3, and that's the choose function. In Desmos, that's going to be NC R, and here we put in 8 and 3, and there's 56 ways unordered. It makes sense that there's more ordered ways than unordered ways, but that's our next important function here, is the choose. All right. Let's see if we could see that again here. 5 names are written on slips of paper and put in a hat. 3 names are drawn and written down in order. How many ways are there to do this? Think about that. What's this one? Does the order matter? Yes, this is going to be permutations of 5 things taken 3 at a time. I'll let you calculate that on your own. I think we did it in the last slides. This is the number of ways. Oh, so it's 60, looks like. All right. Now, but what if we don't care about the order that the names that come out of the hat? We say what? We just who's in the committee. So now what's this going to be? All right, so now this is 8. Oh, no, sorry, not 8. 5. I got 5 people. I'm choosing 3. And that's how generally, I think, in general, just that's how this turns out to be 5 times 2, 10. 10 ways. Again, now we just use Desmos to calculate that. So I like to think about these as, all right, I have 5 things in a bag. How many ways can I reach in and choose 3? That's how I think about these choose functions. Okay. And this is going over just what we said. How do we do it? We just divide by that factor of 3 factorial. Sorry about that. And in general, here's our combination. This is the choose, right? Make sure there's no line when we do combinations. I know we're used to the fraction line. This is the formula. It's kind of nice to see. I want you to use Desmos every time to find it, but this is the formula. And I want to note a couple ones that are maybe nice and easy to not put in Desmos. Okay, so we have n choose 0 always equals 1, and then it's also equal to n choose n minus 1. And then n choose 1 equals n, which is equal, oh, sorry, go back here. N choose 0 equals 1, which is equal to n choose n. And n choose 1 equals n, which is equal to n choose n minus 1. It's just an easy replacement. You could use Desmos if you want, but when you see n choose 1, writing the number n is much easier. All right? And remember, what are we doing? We're taking our permutations with n things taken r at a time, and we're taking out that order, meaning We're reaching into a bag and grabbing a bag of N things and taking out R things. Whereas the permutations of N, comma R that's the number of ways to order R things that I pull out of the bag. How many ways are there to select a committee of 5 senators? Note that there's a total of 50 senators. Hit pause and think about this for a minute. This is a combination. This is going to be 50 choose 5. Let's check Desmos for what that is. 50 choose 5. Looks like 2,118,760. Okay. Now, let's say I'm going to a job interview. I have 3 blazers, 6 shirts, 4 ties, and 4 pairs of slacks. Which would be appropriate to wear? They would all be appropriate to wear together. How many possible outfits do I have to choose from? Okay, I want you to think about this for a minute, but this is... What do we have to be careful of when we're doing is, this is, there's not really an ordering, but there's a categories. There's 3 ways to choose blazers. There's 6 ways to choose shirts, 4 ways ties, and 4 ways socks. Okay, so that comes out to be. That means I use the that's is the multiplication principle here. 3 times 6 times 4 times 4. Let's just double check what that is. 3 times 6 times 4 times 4. 288. 288. Now, I put this in this, it's not a combinations one, and it's because we have to be very careful. We got to get used to being able to distinguish from using combinations and using permutations. That's a major part here, and so that's why I wanted to slip on that are not combinations. How about conference in 9 schools? How many interconference football games are played during the season? Teams shall all play each other exactly once. Now here, right, we could actually do this a couple ways. Well, we could do, there's 9 ways to pick the first team, 8 ways to pick the second team. Oh, but notice what that's gonna do counting is, say the Tigers are gonna play the Cardinals. Oh, but you'd also count CT. We only want to know exactly once, so we'd have to take 9 times 8 and divide it by 2 because we want these two to be the same. Another way to think about that is, they want to play exactly once. That's how many ways can I pick 2 teams from 9? And those in fact are equal. And we see we come with 36. All right, so sometimes we could get to it either way, but it's important to understand what we're counting there. Space shuttle crew consists of a shuttle commander, a pilot, and 3 engineers. The shuttle commander and the pilot are to be chosen from 8 candidates, and the 3 engineers are chosen from 12 candidates. How many such space shuttle crews can be formed? I want you to think about this for a minute. Okay, send me an email if you're unsure before you go back and watch the video. All right, so here, I think this is a little bit of mixture. We need to, how many ways we could pick the shuttle commander, and then we have the pilot, and then we have, notice the engineers are not distinguishable from each other. Okay, so how many ways is there to choose the shuttle commander? 8, and then once you choose that, there's 7 ways to choose the pilot commander. Okay, And then the engineers now, what are we doing? We're choosing 3 from 12. So that's going to be 12 choose 3. All right. And so we get 8 times 7 times 12 choose 3. I'll let you calculate that on your own. But I do want to say the same thing as the permutations of 8 things taken 2 at a time times 12 choose 3 if you wanted to do it together. Right. Okay. Lastly, what's the probability of 4 heads when tossing 10 coins? Okay, so now this is kind of a preview of what's coming in the next section. But here, first of all, whenever we're doing probability tossing coins, first thing we want to do is find the size of the sample space. And since we're doing it counting, we want to make sure, just like in the previous unit, we're going to have equally likely outcomes. And we do that by thinking of it ordered. So here, what's the size of our sample space? Hopefully you all see this. But there's 2 ways that the first coin could come up, 2 ways that the second, third, fourth, and so on all the way out to the 10th. And this is really we get 2 to the 10th. And this is why there's 2 ways. There's a Venn diagram going on under here, just like before, but we're getting better at imagining further out, and it's going to go out 10 places. And in the end, you'd have 2 to the 10th branches. This is what this is telling us. All right, so now let's say E is the event of getting 4 heads. All right. E is event getting 4 heads. Okay. Now think about what this is. We could think of it, we want to know how many ways we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? What does this come down to getting 4 heads? How many ways can I choose 4 from these things? If we think of this as 1, 2, 3, 4, 5, all the way out to 10. We could think of this as we have the numbers from 1 through 10 written on pieces of paper, and we put them in a hat. How many ways can I reach in there and pick out 4 numbers? Because what does each of those 4 numbers represent? Let's say I picked out 1, 2, 3, 4. That would represent getting heads on these first 4 flips. Okay. Oh, so I'm going in, picking out. There's 10 items, and I'm picking out 4. So we get the size of E equals 10 choose 4. And finally, we get that the probability of event E getting 4 heads is 10 choose 4 divided by 2 to the 10th. Okay, and we can look at what this equals over here. That's going to be NCR. It's 10 choose 4 divided by 2 to the 10th. Oh, I misplaced the parentheses there. Here we go. And it looks like it's about 0.2051. All right. So that tells us, no, that's how to actually calculate it. But how do we use that in our thinking? Because remember, this class is about thinking about decision making. And here, what this tells me is something like this, an event that happens like this with a about 20% chance of happening, I'm not that surprised if it happens. So if someone's flipping coins and they get 4 heads, it doesn't make me think that the coin has anything wrong with it. It seems fairly reasonable for that to come up. If it was something like, a 0.002% of it happening, I'd be skeptical. All right, so I want you to think a little bit about that and remember that we're counting because it's going to help us with probability, which is the next unit and video. All right, have a great day, and please let me know if you have any questions.